Yo, what is up, YouTube? It's your boy Big Stacks, for me all underscore 1K, and today we're going to be deriving the equations of motion the same way Newton did it over 300 years ago. So this is a very important skill you need to know if you're a physics major going to college. They make you do this in your physics 1 course, and yeah, let's just get straight to it. So the first derivation is actually the simplest one of them all. Comes from Newton's second law of motion. Force equals mass times acceleration, a very linear relationship between the two, but it can take you very far in terms of calculus with physics. And so what we're going to do is we're going to rewrite acceleration in terms of its first derivative. So acceleration, as we know, its first derivative would be the rate of change of velocity with respect to the rate of change of time. So we can rewrite this as a times the rate of change of time is equal to the rate of change of velocity. So now we have a differential equation, boys. We're going to relate the original function to its derivative, but we're going to do that by using an integral. So an integral here, our first portion is going to be with integrating with respect to time, and obviously since this is the real world, we can't have a negative time, so we're going to start at a time of 0 to some time t, and we're just going to put in what we're integrating acceleration with respect to time. Of course, that's going to be equal to the integral for our rate of change of velocity. So the integral is going to be integrating with respect to time, and you're going to start at some initial velocity and end at some final velocity. And of course, we're integrating with respect to time. Now, for this first integral here, if we plug in the values and we evaluate the integral the same way we do with every other definite integral, you literally just get a times t. And for our second integral, if you plug in our values, you would just get VF minus VI. So we can see that we get VF equals VI plus AT. And we can check our work by, never mind, I forget how you, oh, never mind. So acceleration VF minus VI over T. Acceleration is the difference in velocity over time. So we checked our work there for the first one. Bada bing, bada boom. Yo, what is up? We back. Alright, so our next equation, we're actually going to have to use what we just figured out here for our first equation. So let's just write that down again so we don't forget. And our second equation, well, we're just going to build off of this right here. So we know that velocity, its first derivative is the rate of change of position with respect to the rate of change of time. So we're going to rewrite this again as v times the rate of change of time is equal to the rate of change of position. And you can already see where this is going if you know calculus and you just look at our last step. So we're going to take the integral. Again, we're integrating with respect to time, so it has to be from 0 to t. And then our function on the inside, we're actually going to swap out this v here with this inside here, plus at, and then integrating with respect to time, and make that equal to the second integral. This is position, so we can just have an initial position and a final position, and integrating with respect to time. So we're going to have to actually take the antiderivative of this function. Now there's actually something inside the integral here. So the antiderivative of this function would literally just be vi times t plus 1/2 at squared. This is obviously a very simple polynomial rule if you've taken calculus. That is square one right there. And so for this second integral, we have x position final minus x position initial. And the difference in the x's is literally just the displacement. So already we have our second kinematic equation. So for our final derivation, we're just going to remind ourselves of the two derivatives for acceleration and velocity that we just came up with. So acceleration's derivative is the rate of change of velocity with respect to the rate of change of time. And velocity's derivative is the rate of change of position with respect to the rate of change of time. So now we're just going to solve for dt on both sides. So obviously dt on this side is going to be dv over a, and dt here is going to be dx over v. Okay, so now that we have these two derivatives written out, we can actually relate them because they're both equal to dt. So dv over a is equal to dx over v. Okay, so now we're going to cross multiply, and that gives us v dv equals a dx. And guess what we're going to do again? We're going to integrate once again. So let's scroll down here. So we're going to have the integral of the initial velocity to the final velocity of v dv equal to the integral of the initial position to the final position a dx. Okay, and so we're going to find the antiderivative of this first function because we have a definite integral bounded to its variables. So we're going to get v squared over 2, evaluate from vi to vf. And then for this next one, we're just going to distribute the a to the difference of the x positions. So we're going to have a times x final minus x initial. So finally, we can rewrite out over here 1/2 factored out from vf squared minus vi squared equals a times, change in x. And so now we can multiply that 2 to the other side of the equation equals 2a delta x. And we're just going to add over that initial velocity. So we get vf squared equals vi squared plus 2 times acceleration times change in position, baby. And that is just how Newton did it. He would be proud if he saw us today, still deriving the equations of motion the same way he did it 300 years ago. And what's so special about Newton, actually, is that he wanted to know how objects fell in a gravitational field, but didn't have the mathematics at the time. And so guess what he did? He came up with the mathematics to describe it. And that, my friends, is the beauty of mathematics and its relationship to the physical world. Thank you, and I hope you enjoyed this dick.